Okay, last and certainly not least is Rick Mohr. Rick played an important part in putting the Lustre ecosystem workshop together this year that was sponsored by the Department of Defense. So hats off to you for that. Rock on. Richard Mohr, he's at the University of Tennessee, Knoxville. He's a senior HPC systems administrator, storage team lead at the University of Tennessee's National Institute for Computational Sciences, also known as NICS. Rick was in charge of administering the Lustre file system for Kraken, the first academic petaflop supercomputer. More recently, he's helped design, deploy, and maintain Medusa, the first site-wide Lustre file system at NICS. Ladies and gentlemen, Rick Mohr.
Thanks, Steve. So Steve mentioned I'm from the University of Tennessee, more specifically National Institute for Computational Sciences, which many of you know from the machine we ran, Kraken. So just to clear up the possible question of why I have a bunch of slides that have Oak Ridge National Lab all over them, it's because part of my time is sort of bought out to help work on this progressive file layout project with Oak Ridge National Lab. And as such, I should point out that I'm just one person of a very big team that's working on this. There are several more people at Oak Ridge that are part of this, as well as several people at Intel who are doing the heavy lifting with the coding of the progressive file layout feature. Today I'm going to talk a little bit about the progressive file layouts. I'll start with a brief overview of the current state of Lustre layouts, which I'm sure many of you are all aware of. Talk a little bit about progressive file layouts, or PFL in general, the prototype implementation we have, and the testing that we've done with that prototype. So Lustre file layouts today there are several parameters you can use to control the layouts, but you have the stripe size, you have the stripe count, index, OST pool. In practice, though, most people tend to just tune the stripe size and the stripe count. The way that layouts are handled, there are several constraints. You have a single set of parameters for your entire file. When you choose your parameters, you have to choose it at file creation time because you can't change it after the file is created. And there's really only one type of layout. It's RAID 0. So under an OpenSFS contract, Intel's High Performance Data Division actually produced a new design for file layouts. There's a high-level design document online at the URL shown below, and it covers several different types of layouts: composite layouts, RAID, design for compact layouts, etc. What I'm going to talk about today is actually built using the composite layout design of that document. So the progressive file layout feature is really a way of describing a file layout by a series of components. Each component covers a non-overlapping extent of the file, and each component has its own striping parameters that are set independently. Here I've given a simple example of what a PFL layout might look like. You might say, well, the first 2 megabytes of the file is going to be stripe count 1. After that, up to the 256 megabytes, I'm going to stripe it over 4 OSTs, and then anything after that, I'm just going to stripe over 32 OSTs. Some of the goals for this project were the ability to have a single layout definition that was really suitable for multiple file sizes. Hopefully, you can get reasonable performance for a variety of I/O patterns using a single layout, which is not easy to do today if you have both small files and large files and want to try to use the same stripe count for both. Because the stripe count and the stripe layout can change as the file grows, you can get closer to optimal performance for these things. And it's also a way to simplify Lustre usage for novice users. I'm sure many of us here have seen cases where you set a default layout, and if you set the default to stripe count 1 or 4 or 8 or whatever you choose, there is someone who will come in and not change the default and then create a file that doesn't really work well with that default layout. For advanced users, this just gives them a lot more knobs to tune so they can optimize their performance. And it also opens up features like being able to store different regions of the same file on different types of storage. You could have a OST pool with SSDs as well as regular drives and have your file actually have parts of it reside on both those. And it's also a stepping stone to more features in the future. You know, this is sort of the composite layouts is really the building block for other features that could come down the road, such as being able to do HSM for portions of your file instead of the entire file. Now, the example I showed and even the name progressive file layouts tends to, you know, give this picture of increasing the stripe count as you go along. And while that's probably one of the most obvious use cases for it, it's not really the only one. I should point out that the striping components or the striping parameters for each component are completely independent of each other. And what you really want to do is choose your layout to match the problem that you're trying to solve. Some examples of alternate layouts you might consider, you might want to choose your striping based on the number of processes. Say you had some file, there's a component that's like a shared header that might be read by a lot of processes, and then the second component of your file actually has each process writing its own or reading its own chunk of data. So you might want the second component to scale with the number of processes while the first component is always stripe count 1. Or you might have something you could conceive of where you actually want a decreasing stripe count. You have a component with a large amount of raw data and you somehow post-process it and write the results towards the end of the file. You know, maybe something similar to it, kind of like how you have the round-robin databases that average out data as you go along. So really, it's very flexible and can be used in lots of different ways. Now, the prototype was developed by Intel under a contract from Oak Ridge National Labs, and they delivered it in the first half of 2015 for evaluation and testing. And this is the code that we've been working with over the past year to kind of kick the tires on and test it out. The development is still continuing today. The original prototype didn't have some features such as being able to define a layout on a parent directory and have it inherited by files that were created in that directory. I listed that as continuing development. There's actually been an update. We've just actually taken possession of a code drop that has this feature in it, and we're about to begin testing on it. So there's already been some of that progress has been made. As far as the tests go, there were several different types of tests that were run. Intel ran some tests on their own. They did some streaming IOR and some metadata tests. Compared it with traditional, you know, Lustre striping. They did single and multi-client tests as well as shared file and file per process. Oak Ridge did some tests on their own too. We compared it to something that's called synthetic dynamic striping, and I'll explain a little bit more about what that is later, and ran some object placement tests to compare how the OST object data was spread around the file system for PFL and traditionally striped files. So out of all these tests that were run, I'm only going to present just a sample of them. The Intel tests were actually run on Hyperion, and this kind of describes their IOR test, which is what I'm going to focus on right now. Consisted of a single client file per process with 16 threads. I also did 32 clients for a total of 512 threads, and that was file per process and shared file. And in these tests, each thread would read and write 4 gigabytes of data. So with these, the test layouts that were used in this, we had basically two sort of traditional layouts that represented the extremes, stripe count 1 and stripe count -1, which is all the OSTs in the file system. There was also what they called a PFL small layout, where the entire file was stripe count 1, it had single component. There was also sort of a medium version that was stripe count 1 for 16 megabytes, and everything else was stripe count 4, and then a large one that had, you know, split at 16 megabytes, 128 megabytes, and then at the end of the file it was increased to stripe count 47. So that in total it used 52 OSTs, which were all the OSTs in the file system. So single client IOR file per process performance with the 16 threads. Here we see that some of the things we're looking for right now is sort of a comparison of how we the PFL would work with traditional, in general, you want things like the PFL small and stripe count 1, you would expect those to be about the same. And for reads and writes, that's, they're pretty comparable within, some testing variants. You also see that, the stripe count -1, you expect that to actually be somewhat smaller due to contention than stripe count 1. And then for the sort of intermediate PFL medium layout, you see that the read speeds are better than the stripe count -1. There's a little bit of surprising result in that the write speeds were less than stripe count 1, but you can see that there's some high variance on some of these numbers, which we believe is due to contention within the testing file system. These weren't the only tests going on at the time. If we look at the multi-client, 32-client numbers for the stripe count 1 and the PFL small, we actually see reads are about comparable, and then we see a pretty big discrepancy in the writes, but we also notice that large variance again. Again, we think that's due to contention on the shared file system. And then but we still sort of see that same pattern where stripe count -1 due to contention is less than 1, and then the PFL medium sort of kind of falls somewhere in between. So those were sort of, these basic sanity checks to make sure that things are kind of operating the way we expect it to. And, sort of to finish these out, we had the shared file tests, and this is pretty much what you expect. Something with stripe count 1 just performs horribly. The stripe count -1 is going to give you better results, and if you look at the PFL large, they're nearly identical. So it's operating as expected. As the stripe count increases, you get more performance over the shared file. For the Oak Ridge tests, we had a little test bed, 8 OSS servers, 64 OSTs, a couple MDS servers. This uses the ZFS backend as opposed to the Intel test, which used LDiskFS. One of the things we wanted to look at was a comparison with synthetic dynamic striping. Now, this was prior to the PFL prototype being implemented. There was sort of a simulation done of what the performance might be from dynamic striping. In this case, what they would do is files were split into smaller components, and each component was created in a different directory that had a different default stripe count set on it. So the file was actually split into multiple files, and then the applications were modified to sort of hide that split and make it look like it was operating on one file. For details on the test results, I've included the URL, which describes all the types of tests they did. They included things with IOR and BLAST. The one thing that we looked at with PFL was the IOR tests. Now that we actually had a prototype, we could go back and see, well, before we tried to simulate what would happen, and we got some results. Now that we actually have a prototype that can do this, what kind of results do we achieve? So the IOR test for this was a POSIX shared file test. We had 16 compute nodes, 4 processes each, and the total file size was 4 terabytes. And what we looked at were 6 different striping patterns. There were 3 sort of traditional stripe patterns. The entire file was either stripe count 4, 8, or 16. And then we looked at 3 patterns that used a combination of different components. First one did the first terabyte stripe count 4, the rest did 8. The next one was a 4-16 split, and then the last one was a 4-8-16 over 3 different components of the file. And so these are the results we got for the read and write speeds. I should point out the purpose of the graph is not really to make a direct comparison between the PFL performance and the synthetic dynamic striping, because that's wasn't really the goal. We're not trying to compare this to something that was, merely something that the synthetic dynamic striping was not something you'd use in production anyway. It was just to get an idea of what are the characteristics that we'd expect out of this. So we're really looking at, trends. Particularly see these first 3 are going to be for your traditional Lustre striping. And things like, writes and reads, you see as you add more OSTs, you get this scale-up behavior, When you start talking about the 3 progressive file layouts, the purple and the blue here, we're looking for the same pattern. With the synthetic dynamic striping, we saw this rise and somewhat leveling out, and again, we see that with the PFL, and while, the reads in both sort of scaled up as you added, more OSTs. The PFL version prototype had a newer version of Lustre, which had some performance improvements. But the main point is that we see the same general pattern, and as sort of it's rather fortunate though that not only do we see the same pattern, but the performance for PFL was uniformly better than what we had previously tested with the synthetic dynamic striping. One of the other tests that we did was looked at object placement. It's no surprise to anybody in here who's done Lustre system administration that users often choose poor striping patterns. People create large files with small stripe counts, and then you get imbalanced OST usage or your OST fills up. Likewise, people take small files and stripe them over large numbers of OSTs thinking, well, if one's better, 64 must improve my performance that much. And well, that isn't the case when you want to do a stat or an ls-l or something like that. So PFL can actually be used, can use this increasing stripe count to accommodate multiple file sizes. But what we want to look at is, well, how does using a single layout for all files compared to sort of the ideal case? Our test scenario that we came up with was, well, we want to create a bunch of files that have traditional Lustre striping, and we're going to choose the stripe count on those to be what we consider appropriate values. And then we're going to turn around and sort of use that same file distribution. We're going to create all files with one single PFL layout. And then we're going to look at the OST usage and see how does that look? So first thing that we did was we needed to choose a file size distribution. So we looked at some stats from the Oak Ridge Leadership Computing Facility. And we sort of managed to break it up into 4 buckets based on the file size. So about 70% of the files were about a megabyte, so about 20% are 64, et cetera. And then we chose what we considered sort of a reasonable stripe count for our small test file system. The 1 meg file should be stripe count 1, 64 will do stripe count 4, and the largest ones will go stripe count 48. So that's sort of our ideal test case. And so what we wanted to do was basically for every 100 files, we would create 70 of them that were 1 megabyte stripe count 1, et cetera. And now just repeat that over and over again until our file system reached about 90% capacity. And then we gather our data, wipe the file system out, and then we turn around and created a single PFL layout. And it was broken into 4 components that matched sort of our 4 buckets over here. But every single file that we created would use this exact same layout. There would be no additional changes based on the file size. The 4 terabyte files use the exact same layout as all the 1 megabyte files. And we looked at the OST utilization. So here we have the percent utilization as well as the number of OSTs that were that full. And we actually see that compared to the purple lines show us sort of the ideal case. If everybody did the right thing and chose their stripe counts the way they should, this is kind of how the OST usage would look. And then for the PFL case, where people took the same layout and didn't make any changes at all and just wrote whatever data they wanted to, is the lighter color line, and the distribution is very similar. I think so. This sort of demonstrates the possibility that, if you defined a default layout that was reasonable and a bunch of users hopped on and just started writing files without any consideration, you could actually get somewhat optimal placement of your data on the OSTs. As a system administrator, this is a very appealing feature for me because it means I have the ability to, instead of setting a default stripe count of 2 or 4 on my file system, I can actually create a much more complex layout that changes stripe count as file sizes grow. And so when that person comes in and starts copying over a 4 terabyte file without setting the stripe count from the default, I won't get paged in the middle of the night because my OSTs are filling up anymore. So in general, we've seen that progressive file layouts provide some additional flexibility when defining striping configurations for files. Based on these preliminary tests, and this is just sort of the start of getting into this. We have more tests planned. The performance is looking good. It's on par with traditional Lustre, in some cases better. We've seen that we can use it for a variety of file sizes, which simplifies Lustre usage for users and hopefully saves some headaches for system administrators. For more details on some of the tests I did, since this is just sort of a sample of some of the tests, I'll refer you to a paper that I presented at the Lustre Ecosystem workshop. And like I mentioned, this is just really the start of the progressive file layout work. We've had the prototype and now a newer version of it that has some more of the production level features. We've just got the layout inheritance feature. Things that need to be done are being able to define a PFL layout for the entire default for the file system, as well as some other possible improvements. With the current implementation, each component of the file is basically treated independently. So when you go to allocate your OST objects to those components, it doesn't take into account which objects or which OSTs had been used for previous components, which could potentially lead to some congestion. So could be improvements to the OST allocator that are needed. The other piece that's missing is sort of the dynamic component instantiation. Right now, if you create a file with several components, the MDT will go and it will get objects for all those components, even if you won't write to some of the components at the end. So you only write 1 megabyte to one of these PFL layouts, you've still assigned OST objects to it. And what we really want is to have the ability for the MDT to not assign those until they're needed. Wait until you start writing into that second, third component before bothering to allocate the OSTs. And there's more PFL testing to be done. We want to look at other types of workloads, more data-intensive workloads, as well as increasing the scaling to larger systems beyond these small test beds. And I wanted to thank the Department of Defense for their support of this work, and I'm open to any questions.
Questions for Rick?
When you did the 2 tests that filled up the file system and you looked at your distribution for the OSTs, it was nice that you were comparing against the ideal. Did you do a test where you compared against, we're going to set a 2 or 4 stripe as the default, and everyone's just going to use that?
So we didn't, because the OSTs in this test file system are only 3 terabytes in size. So if we went with the non-ideal case, the first time we wrote a 4 terabyte file with stripe count 1, we fill up an OST and the test would end. So, the non-ideal case is basically the file system melts down the minute we do our first pass, and we run out of space on an OST. So the non-ideal case is not presented just because it would have failed.
I was thinking more along the lines of your default stripe is across 4 or 6 or whatever OSTs, and that's just what everybody uses because nobody touches their code. And
yeah, if we had set a higher default stripe count that was not sort of what you get with Lustre out of the box, then we could have chosen it so that a 4 terabyte file wouldn't have filled up an OST. So no, we didn't do that test. It's definitely something we could easily do.
And then the follow-up is it would be cool to see on the non-ideal test the performance or how long it took to fill up the file system compared to with PFL.
Yeah, we don't have the performance number. Those tests that I ran, I was looking at the OST usage distribution and didn't have the present actual performance numbers on those things too. So.
Anyone else? Rick, thanks a whole lot, man. It's great work.